Yeah, what is this? What? I just some cherries. Oh, are you? Yeah. What? But I can maybe show it to you. That would be fine. You can that too. Sorry? You called me to do the introduction. Okay.
Is this going to make noise?
No, it's quiet.
Where is it pointing?
Look at that. It's pointing at the screen.
So you won't see yourself in there.
No, not during the talk. If it's too far, if I want to capture the entire thing, they can't with the text. So
That's a different level of technology. When you have that and then do a split screen.
oh, I learned to appreciate the guys doing
So
the pros.
is this just recording or is it broadcasting?
Oh, it's broadcasting now, right now. We already have a few viewers.
I want to indicate audience excitement like I should.
Where are the new grad students?
Maybe we should take a walk down and see if any students. Some in 270, I know that.
Is this yours down here? All right, welcome all to Asaf's thesis defense. Pablo will be giving an introduction to him in a second, but let me just remind you what's going to happen is after the introduction, we will have a 50-minute, 45-minute presentation, 50-minute presentation by Asaf. And then members of the public can ask questions. Members of the committee are asked to hold their questions until the private defense will be in another room afterwards. Okay. Cool.
Asaf, it's a bit dark here, but you know, it's the end of the tunnel. It looks like this. And it's just one tunnel, and there's more coming. This has been a long journey for Asaf, for me, for your family too. Before coming to Caltech, Asaf was actually nobody knows. Asaf was part of a secret service in the Israeli army. And, I'm hoping to get him drunk tonight and get some stories from those times. So he came here after spending some time as a graduate student already in Israel. Our connection dates back a couple of generations before you. Alan Rubin in Princeton was my postdoc advisor, who was Alonzi's PhD advisor. Alon and I met in Paris. Then we went our ways. And then after his time in the Secret Services, Asaf became a PhD student with Alon. So this is to tell the new graduate students here that seismology, we are a very tight community. You will make friends, and they will be watching your back. And I can tell you, it's really good to have an Israeli soldier watching your back.
Soldier in the army of peace.
That's a good point. So he came here as a Fulbright fellow, and the first year he was here, he was still a graduate student in Israel. The project we did together, and actually he did by himself, basically, it was a lot of field work looking for tremors in the San Jacinto fault. And by himself, he put together this network of more than 90 seismometers on the ground, organizing a nice crew of other graduate students from the Seismo lab. And from the ground up, he made this beautiful experiment. Of course, we didn't find what we were looking for. That's very typical in research. But despite, we found some other nice things. But despite the frustration, he decided to stay in California. And since then, we've been working together on many things. He will mainly talk today about two of the main achievements of his PhD work. But there are other achievements that I want to mention that will not transpire from your talk. One of them is, of course, the field work in the San Jacinto fault in the data set. The other is his contribution to the back projection work that we did for the Tohoku earthquake. He's the second co-author in the paper that's the most cited paper of my team here in Caltech. It was the back projection of the results from the Tohoku earthquake. And what Asaf contributed to that work was, well, this was a new technique, and was the first time we were seeing things like this. And we were seeing this from really teleseismic distance. So we had to make sure that this made sense also comparing to the near field data. And that's where Asaf seized that opportunity and took the strong motion data recorded in Japan to compare to the back projection results, to conclude that the big picture was making sense. All right, so Asaf is also a very humble person, and I'm sure that what he's thinking right now is that all the achievements that he will show you today are nothing in comparison with the biggest achievement of becoming a father and raising a beautiful daughter with great values during his PhD. So you're putting the bar very high for all of us, Asaf. Thank you.
All right. Well, okay, thank you, Paulo, for this introduction, and thanks everyone for coming today. Constraining the rheology of crustal faults is essential for understanding earthquake-related processes. In this simple model, the strength of the fault increases linearly with the depth down to about 12 kilometers. Below this depth, it decreases quite rapidly as plastic deformation mechanisms become dominant. While the upper portions of the fault are controlled by brittle processes and fast earthquake slip, the deeper portions are thought to accommodate the tectonic motion by a distributed flow over the long term. The transition from the brittle to the ductile parts of the fault occurs over a zone of finite width. And the talk I will describe to you today, the work that I will describe to you today, focuses on that, on the attributes of that transition zone between the brittle and the ductile parts of faults in the Earth's crust. Because of the limited resolution of geophysical techniques, much of what we know of the structure of deep fault zones comes from exhumed faults at the surface. These deep shear zones contain highly deformed rocks with fine matrix known as myelonites, which are evident to the large pressure, temperatures, and strain that these faults experience at depth. Occasionally, however, these myelonites contain evidence of a fast earthquake slip. That evidence comes in the form of pseudotachelites, veins that contain the melted rock. Some of these veins were overprinted by myelonites, and that kind of observation is usually interpreted as the result of dynamic ruptures that are generated in the brittle part of the fault and propagate down deep into that ductile shear zone. Contrary to this interpretation, in the first part of my talk, I will present evidence for significant seismicity that nucleates at depth at which we think most of the fault motion is being accommodated by ductile processes. In the second part of my talk, I will describe a new methodology that is aimed at resolving the deep transition zone beneath the central section of the San Jacinto fault here in Southern California. This image shows these two faults. The Los Angeles Basin is shown here, the Newport-Inglewood fault and the San Jacinto fault. The Newport-Inglewood fault traverses the metropolitan area of Los Angeles, and the San Jacinto fault runs in the rural area down to next to the Salton Sea. At this point of the talk, it's helpful to compare the seismicity of these two areas. Here I'm plotting the magnitude frequency distributions for the Los Angeles area and for the San Jacinto fault. Note that although the number of stations in the LA area is larger by a factor of 4 than it is near the San Jacinto fault, the catalog magnitude of completeness, which is the magnitude above which all the events are contained are recorded by the network, is larger in LA by 1 unit than it is in the San Jacinto fault. This problem of detection is a direct consequence of a high level of noise within the LA basin, and much of the work I will present in the first part of the talk is aimed at reducing this noise and trying to extract signals that are related to tiny earthquakes that occur along this fault. This is an aerial photo of the fault back in the 1930s. The Newport-Inglewood fault is one of a few fault traces that can very easily be traced at the surface by the location of oil wells distributed along its strike. It's a classical right lateral strike slip fault that slips at about 1 millimeter per year, with a typical an echelon type structure in which fault steps create small compressional areas that uplift areas as this area in downtown Long Beach, known as Signal Hill. This area has been a hub, center for oil production in the Los Angeles basin up until today. And in 2011, a seismic survey took place in that area. This is the fault here, and seismic stations, geophones, were installed inside the city of Long Beach. They're indicated here by the green circles, along local streets and in backyards. They were installed for a period of 6 months and comprise what is the densest array to have ever been deployed along an active fault zone. Nodal Seismic and Dan Hollis were generous enough to provide us with this data set, and that data are extremely helpful in resolving the fine geometry of the fault running beneath the array. I'm going to show you a movie of an earthquake wave, seismic waves traversing the array. This is traffic on the main highways. The amplitudes are indicative of the ground motion in the stations, and you can see how seismic waves generated from an event occurring outside the array pass through that area. This is the result of a magnitude 2.5 earthquake, and it's important to keep in mind that we're looking for a much smaller event events than that. Our target magnitude for detection is about magnitude 0 below, and most of the signals that we are recording here are not well resolved, and the signals from this tiny earthquake occurring outside the array. Before I describe the methodology, let's have a look at the characteristics of the long-term seismicity on that fault. I'd like to convince you that this fault is somewhat unusual in the environment, in the tectonic environment of Southern California. This is a plot made by L. Huxon. It shows the distribution of focal depth in Southern California against the depth to the Moho. In general, we see that the depth of seismicity is correlated with the thickness of the crust. The deepest events occur in area with thick crusts that are thought to be undergoing strong compression. This compression is thought to be depress the geotherm, thus allowing brittle processes to occur at relatively large depth. Most of the seismicity ceases around the 400 degrees geotherm, where plastic deformation starts to become dominant in quartz-rich rocks. The events I will show you today are outliers on this diagram. They occur in an area with relatively thin crust, but they are deep. They occur at down deep at the lower portions of the crust, as well as in the upper mantle. I will show you today that these events concentrate in that deep shear zone. They concentrate in a narrow zone that is about 1 to 2 kilometers wide. It is located directly beneath the map trace of the Newport-Inglewood Fault in Long Beach. This is, again, the strength envelope that I started my talk with. Vertical axis is depth, the horizontal axis is differential stress. And here I'd like to point the attention of the effect of changing the strain rate in this model. Reducing the strain rate while keeping all the other parameters constant will tend to result in a shallower brittle to ductile transition zone. So slowly deforming faults are expected to contain shallower seismicity. Let's see if the predictions of this model are compatible with the observations from Long Beach. This is the long-term seismicity from the SCSN catalog. The arrays that we've been using are shown here in blue. The warm areas indicate areas with the seismicity clusters, and white areas are areas devoid of seismicity. We're going to make the common assumption that seismicity rate is proportional to a strain rate. And note that as we move from point A to point A prime, the rate of event decreases by a factor of about 70. So there's a 70-fold decrease in seismicity rate or equivalent strain rate as we move along the fault strike. This kind of a decrease should be translated into a resolvable shallowing in the reduction in the maximum depth of seismicity as we move from the northwest part of the fault towards the southeast. In reality, the observation is opposite. These are the same earthquakes projected onto the strike of the fault. You can see as we move southeast along the fault, seismicity becomes more diffuse. It is less associated with the structure of the fault, and yet it deepens, and it occurs at the lower parts of the crust as well as a few events here in the mantle. These are locations from the local catalog I need to mention. And in addition to that trend deepening in the maximum depth of seismicity, we see that the crust is becoming thinner. So there's an anti-correlation between the maximum depth of seismicity and the thickness of the crust, which is unlike most other areas in Southern California. In addition to this observation, there's another piece of information that comes from recent measurements of helium isotopes done along boreholes, deep boreholes along the fault in the LA basin. These indicate that the fraction of mantle material coming out along this fault is relatively high, up to about 70 or 75% fraction of mantle material coming up along this fault. This proportion is extremely high compared to the much more tectonically active San Andreas fault. We're going to use these two arrays to illuminate the deep structure of the fault, which these observations suggest acts as a deep conduit, moving fluids from the upper portions of the mantle into the shallow crust. We're dealing with very noisy recordings. This is a typical record section containing several hundred traces. Time here is on the horizontal axis. And we're unable to see these events on a single trace. Now, these 90 seconds contain several events, but by looking only on a single trace, we cannot see them. We're going to use the fact that we are able to resolve that entire wave field with the array and apply traditional techniques from migration, techniques that were developed mainly in the oil industry to try to significantly improve the power of the signal in our recordings. This schematic shows how our technique works. The array is situated at the surface, and the recordings at the stations are dominated by a random surface wave noise. Imagine that an earthquake occurs at depth and emits wavefronts that are recorded at the surface by our array. Now depth is increasing in that direction, and time is increasing in the vertical direction. These waves make their way up into the station, to the surface, and are recorded by the array, but their signal is masked by the noise. We are able to solve the wave equation backwards in time and propagate these waves into the point of origin. This technique is called phase migration, and it is heavily used in the oil industry, and it has a twofold effect. The first one is that it tends to focus back the energy onto the point of origin. And the second, that it tends to diffuse away uncorrelated noise at the surface. Let's have a look at the effect of this technique on our recordings. These are the recordings at the surface, and these are the recordings at the depth of 5 kilometers. The X here indicates an epicenter of a magnitude 0.4 event that occurred directly beneath the array. You can see how spherical wavefronts propagate away from this point. This kind of indication is a sign that an earthquake was actually recorded by this array. At the surface, there's no signal whatsoever that an event occurred beneath the array. Sorry. Yeah. Here I'm showing again the same record section at the surface and at the depth of 5 kilometers after it has been migrated to depth. And you can start seeing these move-outs, these vertical lines crossing that cross-section. These are these are phases that are a result of small, tiny earthquakes occurring beneath the array. The reason that they are almost vertical is that they are deep and they hit most of the sensors almost simultaneously. Note that, again, at the surface, there's no indication that several of these events were recorded by the array, and only after we migrate that wave field, this pattern emerges. These are the locations. Here I'm showing the event density beneath the Long Beach array. for events which occur at a depth of 5 and 12 kilometers. The red areas indicate seismicity clusters, intense seismicity, and the yellow areas are areas that are devoid of seismicity. The counts here were normalized by the maximum number of events in that depth range. Note that at shallow depth, we don't see any correlation between the map trace of the fault and seismicity in that area, nor do we see any much correlation with activity in the nearby oil fields. As we increase the depth of that section, seismicity progressively concentrates until at a depth of 20 to 32 kilometers, it localizes onto a narrow zone of seismically active deformation that is located directly beneath the Newport-Inglewood fault. This zone is about 2 kilometers, 1 to 2 kilometers wide, and the uncertainty on the locations of the event assures us that width is actually a robust estimation, is estimated robustly. Up to 90% of the deformation in that zone, using the long-term geologic slip rate on that fault, is accommodated by aseismic processes. This is a vertical cross-section perpendicular to the fault, and it shows very nicely how seismicity crosses the entire crust and enters into the lithospheric mantle beneath Long Beach. We have looked at recordings from the nearby Rosecrans Array, located only 15 kilometers to the northwest. And over there, we were not able to see this deep localized shear zone. This indicates that the lateral extent of that zone cannot exceed about 15 kilometers along the fault strike. The caveat here is that we're only analyzing data from a short period, a short interval, compared to the recurrence interval of large earthquakes on that fault, which is several hundred years. I remind you that it's a very slowly deforming fault. And so that feature may be the result of a transient, and it is actually very hard for us to tell if this is actually a representative of the long-term deformation along this fault. These are the distribution of event depth. Note that the number of events decreases very rapidly with depth. This is one reason why these deep earthquakes are not, most of them are not being picked up by the local network. The second reason is that their size distribution is different than the events at the shallow portions of the fault, and I want to elaborate a little bit about this point now. These are again the frequency magnitude distributions, magnitude here and the horizontal axis and the logarithmic counts on the vertical axis. These are our results, the blue lines, the blue squares. The green squares indicate the SCSN counts for 30 years, normalized by the space and time windows associated with the Long Beach experiment. Note that most of these events fall on a single, most of these measurements fall on a single one, which indicates that the B value is approximately 1. Also note that we were able to reduce the catalog magnitude of completeness for these shallow events by about 2 units or even more. This is the same plot for the deep event counts, and note that their numbers fall off much more rapidly with their magnitude than they do for the shallower seismicity. Here I'm going to plot these measurements on a different scale. This is a semi-logarithmic scale showing, again, the event counts on a vertical axis against their amplitude, which is proportional to their moment. On this type of, on a semi-logarithmic scale, an exponential distribution should plot linearly. And this is what we see for the deep events in Long Beach. While the shallow events are well fitted by power law. So the transition from the shallow to the deep portions of the fault exerts a strong influence on the distribution of seismicity, a transition from a power law distribution in the size of events to what appears to be an exponential distribution. And I would like to propose a conceptual model that is capable of capturing the first order observations that we see in this data set. In this model, the change in the b-value or in the event size distribution is thought to be controlled by the level of interaction between events. The shallow portions of the fault, we think of them as areas of strong earthquake interaction, strong event interaction. The deeper portions are thought to be areas of weak interactions. The first variant of this model is controlled by the rheology. Here, seismicity nucleates on velocity weakening patches that are embedded in a velocity strengthening matrix. Each rupture can propagate some distance into the velocity strengthening area, and thus encompass several of these asperities. If with increasing depth, the stress drop inside the asperities becomes smaller, or the area surrounding them becomes more velocity strengthening, and thus more prohibitive towards rupture, the final size of these earthquakes will be limited to the size of the asperities they nucleated on. If these asperities are exponentially distributed, that will give rise to the limited size distribution that we observe in Long Beach. The second variant is controlled by the geometry. Here, all the physical properties remain the same, but the average interasperity distance, a parameter we define as is defined here, increases with increasing depth. In that case, just because the asperities are farther away from each other, it will be more difficult for them to interact. Thus, they will be more confined to the size of the asperities they nucleated on. In reality, what is important is a 9-dimensional number, which is the ratio of the rheology or the geometry or the asperities radius of influence over the average interasperity distance. We cannot resolve each of these parameters independently, but for the population in Long Beach, we can say with a high level of certainty that this ratio decreases with increasing depth along the Newport-Inglewood fault segment. These are the conclusions for the first part of the talk. The seismicity on the Newport-Inglewood fault extends to the lower crust and the upper mantle. This transition from a strong to weak interaction regime is characterized by the localization of seismicity, a narrow earthquake size distribution, and a reduction in temporal clustering. Our observations are consistent with a model in which tectonic motion at the root of the Newport-Inglewood fault is predominantly supported by aseismic ductal flow, but interspersed by seismogenic asperities. In this framework, the ratio between the radius of influence and the interasperity distance becomes smaller with increasing depth beneath Long Beach. In the second part of my talk, I would like to describe a methodology whose objective is to characterize pattern of seismic and aseismic strain accumulation along the deep transition zone beneath the San Jacinto fault. This is the most seismically active fault in Southern California, with 11 magnitude larger than 6 earthquakes occurring along it in the past 150 years. Note that unlike the Southern San Andreas fault, seismicity in the San Jacinto fault is more or less correlated with that fault structure running right here. The colors of these stars indicates the main shock time. And note that in the past 10 to 15 years, we saw a substantial increase in the rate of moderate earthquakes on this section of the fault near Anza. These events nucleate at a relatively large depth of about 13 to 14 kilometers and generate prolonged aftershock sequences as well as very strong aftersleep. The maximum depth of seismicity in that area is about 16 kilometers, while the locking depth inferred from geodesy is only 12 or 13 kilometers. That discrepancy between the geodetically inferred locking depth and the actual maximum depth of seismicity led Widowinsky to propose that that fault is being loaded by a deep creep zone beneath that area, that section of the fault. That creep is loading seismogenic asperities that eventually break during these moderate earthquakes. We're going to test this hypothesis using sensitive strain meter data located around the fault, as well as the timing and locations of these events and their aftershocks. This is an attempt made by Eric Lindsay et al. To see how much of this variability at depth can actually be resolved from the available geodetic data sets, namely GPS and INSAR. Here, these are surface velocities plotted with respect to distance away, normal to the fault. And so these are these observations. And the color lines indicate the predictions from 3 models for the variation of slip rate at depth. Note that these 3 very different profiles give rise to identical predictions at the surface. Thus, that indicates that the sensitivity of the geodetic data set to the actual details of slip at depth is very low, essentially 0. To be able to resolve that, one could use, or to better resolve that, one could use the timing and locations of events, as well as more sensitive geodetic measurements that are available for this fault. And here I'm plotting again a zoom in on the Anza section of the fault. This is the seismicity associated with some of these local main shocks. This is the well-known Anza seismic gap, a term that was coined in a paper by Sanders and Kanamori back in 1984. And we have a network of very sensitive borehole strain meters located along this, near that section of the fault. These strain meters record periods of accelerated slip on that fault that are the result of local as well as remote main shocks. Here I'm plotting the shear strain at one of these stations. The horizontal axis is time in days. And for 4 different periods, the top is the period following the distant El Mayo Kukapa earthquake, and the 3 at the bottom are due to moderate earthquakes in the southern part of the Anza Gap in Anza, on the Anza Gap on this section. First, note that the maximum strain change at the measured by this instrument is only about 200 nanostrain. That translates to a tiny length change at the surface, well below the resolution of the GPS network in Anza. Another interesting feature that is seen by these records are the proportions of the core and the post-seismic strains associated with them. For these 3 curves, I'm plotting the core and the post-seismic strain change. Note that the co-seismic strain change should appear as a step on these records. And we can hardly see any change in strain that is associated with the rupture of these local main shocks. most of this strain is being released in the post-seismic period during the days and weeks following these events. The second piece of information comes from seismicity. Here I'm plotting events projected onto the fault, the plane of the fault. This is distance along strike, and that's time, logarithmic time in days. Note that the events following one of these main shocks, which nucleated here, propagate very fast outside that region. These dashed curves indicate migration velocities that are proportional to 1/time, where time is measured since the main shock. So as we see in the strain data, the aftershock expansion starts very fast and then it decays. Another thing that we're seeing is that seismicity is being triggered very far compared to the size of these main shocks. So magnitude 5.4 is expected to exert insignificant static stress changes at distance that are 30 or 40 kilometers away. Because we're seeing a very strong strain signal at the surface associated with the post-seismic slip, a natural candidate for modeling this kind of process is to associate that triggering with triggered creep following the main shock. So now I'll show you how we can combine both strain and earthquakes to better resolve slip on that fault. I want to mention that the development of this methodology is heavily relying on previous work made by Alon Ziv, who's also assistant, has helped tremendously in the developments that I will show now. We know that co-seismic or slip, co-seismic or post-seismic slip changes the stress in the area surrounding that fault. Some areas will undergo stress increase, Coulomb stress change, which is positive. If they contain seismically active faults, these faults will be pushed towards a failure and will generally produce an aftershock sequence that decay according to the modified Omori law. The reverse is true for areas that experience a negative stress change, that they will be pushed away from failure and will slowly go back to the long-term seismicity rate on that fault. These are the type of observations that we see, and that is the type of data that we wish to infer. In reality, we do not observe stress changes. We can only see changes in the rate of seismicity. To relate changes in the seismicity rate to changes in stress, we are using an aftershock model derived by Jim Dietrich. This model, seismicity, nucleates on rate and state faults that are velocity weakening and are already approaching or accelerating towards failure. A strong assumption here is that the nucleation sites are not interacting. Through this study, we have confirmed that this assumption is valid for modeling the seismicity in ANZA. Our assumption, in addition to that, is that most of the seismicity is being triggered at off-fault sites due to aseismic creep occurring on a principal slip zone. This is a schematic showing the setup of the problem. The strain data at the surface is used together with stress changes at depth that we infer on patches outside the fault zone, noted here in gray. These measurements at the surface, together with the stresses, the inferred stresses, are jointly inverted for this distribution of fault slip that can satisfy both these data sets. These are the slip distributions for the first 10 days following two events in 2010, the El Mayo Kukapa and the Collins Valley earthquake that happened 94 days following this event. Note that after slip is deep. Most of it occurs at depth of between 12 to 15 kilometers, and it wraps around the rim of two large clusters of seismicity located on both sides of the gap. The stress drops that are associated with this aftersleep are relatively large. They're 10, even 100 times larger than the stress drops associated with the, for example, slow sleep events in Cascadia. This is an outcome of this of a very patchy sleep distribution that is necessary in order to satisfy that patchy distribution of seismicity. It is interesting to compare these two sleep episodes. Here I'm plotting sleep contours for the 2010 episodes. Note that they are complementary. The aftersleep generated by the local Collins Valley is complementary to the distribution of aftersleep triggered by the distant El Mayor Cucapa earthquake. This is reminiscent of the activity of the behavior of large earthquakes, where one earthquake ruptures a fault gap left behind by previous events, and it is indicative of some causal relation between these two episodes. The next question I'd like to answer is whether the magnitude 5.4 Collins Valley main shock was triggered by aftersleep induced by the El Mayor main shock, which occurred 94 days before the local main shock. To do that, I will first compare the distribution of on-fault stresses that are a result of these sleep distributions. You can see that aftersleep from this local main shock propagates mainly into areas that were highly stressed by the post-seismic sleep from El Mayor. It does not peak close to the main shock. It peaks far away from it near the Anza Gap. These are plotted only for 10 days of post-seismic strains and aftershocks. I'd like to see if there's any indication in the long-term seismicity rates of any change on the activity of the fault that is compatible with such a scenario. Here I'm plotting the event rates. These are the vertical lines and the cumulative number of events in Anza. This is the time of the El Mayor Cucapa earthquake. And note that seismicity rate increases by about a factor of 10 relative to the pre-event rates, and it remains high up to the rupture of the Collins Valley earthquake. Also, note that what we can see on the strain meter data for this period is a very fast strain change associated with the first few days, and then flattening of the strain records, plateau. The inference that we make based on these observations is that post-seismic sleep induced by the El Mayor Cucapa earthquake initially propagated very fast and then remained relatively stationary, thus stressing nearby asperity or nearby earthquake clusters, producing that sharp increase that we see for additional 80 days up to the Collins Valley main shock. Let's see if this scenario is compatible with a long fault seismicity rates and stresses. Here I'm plotting the seismicity rates along strike at locations of the fault trace for the second week after the El Mayor Cucapa earthquake and for the rest of the period leading to the Collins Valley main shock. Note that these two patterns are correlated. If aftersleep would have migrated continuously at the same rate it did during the first few days after the El Mayor Cucapa earthquake, we would expect seismicity to propagate together with it, and it would not be correlated with the early seismicity generated by aftersleep from this sequence. Here I'm plotting the stresses that we infer based on these stress distributions, and these stresses are relatively high. They reach almost 1 MPa at the location of the Collins Valley main shock. This is about 50 times larger than the cumulative stresses that would have resulted in that area just due to continuous slip on a dislocation buried at a depth of 16 kilometers. So our conclusion from this part of the talk is that the El Mayo Cucapa earthquake initiated a several months long transient along the central section of the San Jacinto Fault near Anza. The aftersleep generated by the 2010 main shocks has little overlap. This type of complementarity is also seen in sequences of large earthquakes. The joint data sets requires aftersleep to occur at the edges of the two large clusters of seismicity, as well as beneath the Anza gap. And the end result is that this aftersleep causes a significant stress change within the gap itself. The stresses that we infer from seismicity leading to the Collins Valley main shock suggest that this earthquake was triggered by stresses imposed by the El Mayo Cucapa remote aftersleep. Here I will end the research part of my talk, and I would like to show you a short movie that I have presented, that I have prepared for this demonstration. If you're watching this on YouTube, I'm going to turn down the sound for a few minutes, and then we'll be back on broadcasting. Okay, so just give me a second here to
either check.
I have a question on the first part. What the events that you detect, the deep events, what does it imply on the attenuation structure? What I mean is, what's the minimum attenuation that would allow information actually to propagate from such small events that are so deep and reach the surface instrument?
I can tell you what are the results of our synthetic tests using the attenuation structure for Southern California. And this indicates that we cannot reliably detect events whose magnitude is lower than about 2 if they occur at a depth of 30 kilometers. And events that are lower than about, or a range of about 1 to 2 at a depth of about 20 kilometers. This is the detection threshold using the attenuation structure for Southern California. Perhaps with more sophisticated techniques, we can go even smaller.
Well, I mean, you did detect events that were smaller and deeper.
Yes, yes, but that's the bound.
And you use non-traditional techniques, I understand. But information did still had to propagate. Right?
That's true.
So that still gives us, there must be, I mean, I'm just saying, this tells us something about the cube.
You need to know about the high frequency source radiation, which requires some very big assumptions.
Under any assumptions, I mean, so there's a small events, particular events that satisfy some kind of conceptual model that you have. I'm just saying we could use this to try to predict minimum Q structure, and then see if that would allow the information to propagate.
Yes,
And then ask ourselves,
I agree.
this.
Yeah. So we've done wave propagation with the available Q structure, and added the noise that we have in the back projection images, and that gives us some bound. But I agree that you could improve on that. You can get a better attenuation structure just by looking at asking how can these events solve for the attenuation structure instead, which is something we did not do.
I had a question about the first part also. Given the aperture of the array, which is, let's say, 5 to 10 kilometers, I'm a bit surprised that the resolution of your detections doesn't decrease when you go to depths much larger than the aperture of the array. 30 kilometers.
It does decrease. Yeah, it does decrease. It does, but we've done a series of synthetic tests to see what are the uncertainties on the event locations, and they generally increase with depth and with a reduction in the size of the events. So we cannot reliably locate very small events at large depth. We can perhaps detect them, but we cannot locate them very well. So it becomes too blurry. So most of the range of magnitudes that we can still detect at that depth, I mean, the uncertainties are on the depth for 25 to 30 kilometers range is about 5 kilometers in the vertical and about 2 kilometers or less than 2 kilometers in the horizontal. It gives us some bounds on the width of that zone of deformation.
Regarding the same result, I think the map of deep events showed a concentration in the northeast.
Yes.
Part
Yeah.
of that result.
That's true. It's part of a structure that we noted as well, and we elaborated a little bit on that in the paper. Because it's located towards the edge of the array, it's very hard to resolve it. We are only focusing on events that occur right beneath the array, because for these events we can very significantly increase the signal-to-noise ratio and constrain the locations relatively well.
Any other questions? Thank you.
So as far as the frequency magnitude statistics for the detected event, so if you think any variation in that could be resulting from limited sampling over a short period of time, then how do you know that it's not just from that?
So yeah, as I mentioned, we might be seeing a transient. And we know from other faults that sometimes during transients, the B value changes. Might decrease, for example, during a swarm. But that's as much as we could say. We don't have data outside these time windows, so this might not be characteristic of the longer-term deformation on that fault.
Okay, well, just take us off again.
Thank you. Thanks.
Yeah, bring your computer.
I will. Thank you. Like Antonit. אוי, מה יש לך? באתי עם על אופניים. Este papi.
Casi, papi.
¿Viste lo que hizo, papi? Thanks a lot. Thank you.
How are you?
Congratulations to you as well. To you as well.
Yes.
Good job. When you're busy?
Sí.
Okay. Sí, שעושה. כן. יהודה.
נעים לשמוע עברית, סרט מוזר קצת, אני חייב להגיד. מה זה הסרט הזה?
זה פרק מספר של סופר צרפתי יהודי ששמו ז'ורז' פרק, שגר בפריז.
כל הדבר הזה זה על יוטיוב? כל הספר?
לא, הספר...
הסרט זה חלק מהספר.
לא, אני לקחתי את הפרק הזה, הקלטתי את עצמי, קורא אותו, וערכתי את הסרט. כבוד האירוע.
הסרט הוא שלך?
כן.
אתה אוהב את אני אומר, זה קצת מוזר.
זה סיפור מוזר, אני מסכים. יש פה תפיסה פילוסופית מסוימת, שהיא מעניינת אותי.
לא שמעתי על זה. איך אוקיי, אתה תפתח.
אבל אני אשלח לך את הלינק, זה גם, אם אתה מקיש אסף אינבל ביוטיוב, אז החלק השני של כל החלק הזה שהתנתי מופיע שם.
שלח לי אימייל על כל הדברים האלה.
בסדר.
עם הלינקס. עכשיו, מה זה הסיקרט סרוויס הזה שהאמפוארו דיבר עליו?
אנחנו מצלמים ביוטיוב, רגע, אני אעצור את השידור. צ'יצ'י. עמליה.
איך?
עמליה.
עמליה.
כן. אעצור את השידור.
עמליה, how are you, עמליה? Shy, as usual?